structural, electrical, and optical studies of ZnO/TiO2 thin films fabricated by RF sputtering process for UV application. Abstract: ZnO-based nanostructure composites are eye-catching for high-tech applications of energy conversion due to wide range in operating potential window. ZnO are regarded as one of the most capable candidates for UV photodetectors due to its wide band gap, strong radiation, and high chemical stability. This study presents about fabrication of p-ZnO/TiO2 layer via radio frequency, RF, sputtering. This article reports fabrication, structural, optical, electrical and microstructural characterization of nanostructured p-ZnO/TiO2 films. Nanostructured zinc oxide, ZnO, thin film was deposited on aluminum-coated glass substrates using radio frequency, RF, sputtering process for fabricating p-ZnO/TiO2 thin films. After deposition, these films are annealed at 523 K. Structural properties, surface morphology, and quality of thin film have been studied using XRD, Afm, FE-SEM and energy dispersive X-ray spectroscope, Edx Measurements.The optical property of the deposited nanostructured p-ZnO and TiO2 thin films on the glass substrate were characterized on the ultraviolet spectroscopy, UV-Vis spectroscopy. XRD measurements revealed the formation of ZnO and TiO2.XRD analysis confirms the formation of pure crystalline form. The average crystallite size of as deposited nanostructured ZnO and TiO2 thin film was found to be 29 nm and 20.7 nm respectively. The junction properties of p-ZnO/TiO2 were investigated using current voltage measurements. The current was analyzed by sweeping the voltage from -5V to +5V and the knee voltage was found to be around 1.58V. The abrupt absorption on 328 nm wavelength was seen for both of the deposited films. Keyword: thin films, microstructural, RF sputtering, ZnO/TiO2, photodetectors. 1. Introduction. Wide bandgap semiconductors are extensively used in ultraviolet, UV, detectors, particularly oxide semiconductors such as ZnO and TiO2, which are environmentally friendly as well as chemically and thermally stable in harsh environment. UV photodetectors have been extensively used in a variety of commercial and military applications, such as flame sensing, secure space-to-space communications, pollution monitoring, and early missile plume detection, etc. 1 to 3. These applications require extremely sensitive devices with high response speed and high signal-to-noise ratio. Nowadays, a range of UV detectors are available, mainly Si-based photodetectors. However, Si-based photodetectors have considerable limitations, such as the need of filters to stop low-energy photons, visible and IR light, and lower efficiency. To stay away from these disadvantages, UV detectors based on large bandgap semiconductors have received more and more concentration due to their intrinsic visible blindness. Moreover, materials with large bandgap are chemically and thermally more stable compared with the material with narrow bandgap, which make it capable for operating in harsh environments. A striking approach to improve efficiency and diminish costs of modern hybrid photovoltaics is the application of nanostructured metal oxides thin film such as TiO2. Crystalline structure of TiO2 exists mainly in three forms such as anatase, rutile, and bruchite. Anatase form offers much advanced photoactivity than that of rutile. Amongst the different materials studied thus far, titanium dioxide, TiO2, an N-type semiconductor, anatase 3.2 eV and rutile 3.0 eV, has an extremely wide range of application field due to the ease it can be used to fabricate various one-dimensional nanostructures. ZnO as well as their nanocomposite forms 5 to 7. The N-type character in these semiconductors originates from the large density of oxygen vacancies generally detected on the surface of these nanostructured materials. In turn, these vacancies change the material's chemical reactivity and stability by providing electron trap sites, causing electron-hole recombination during operation of the device. To overcome this limitation, nitrogen doping has been the preferred method, with various approaches employed, such as chemical doping during synthesis. It is well known that the donor-like defects such as oxygen vacancy and Zn interstitial are easily formed in the ZnO, which leads to natural N-type doping. From an electronic point of analysis, TiO2 and ZnO are the best semiconductor candidates. Indeed, the valence band and the conduction band of ZnO are constituted of d orbitals and sp hybrid orbitals respectively. TiO2 is constituted of p orbitals hybridized with d orbitals in the valence band and of d orbitals only in the conduction band. These two configurations are in support of an efficient electron-hole pair promotion 8. In some studies, ZnO has a lower rate of recombination compared to TiO2 9,10 among many metal oxide semiconductors, the beneficial properties of zinc oxide. ZnO, such as high carrier charge mobility, and environmental robustness, have attracted significant interest for application in semiconductor devices. 11. The broad band gap, 3.37 eV, better transparency, high charge mobility, high thermal stability and low synthesis cost are some of the key factors which make it suitable for fabrication of various optoelectronic devices and applications. In order to increase the efficiency of the sensor, different methods such as surface treatment and covering by other materials have been used by several groups. 8 to 20. ZnO-based nanostructures have a wide range of high-tech application, e.g. photodetectors 12, light-emitting diode 13, photodiodes 14, gas sensors 15, optical modulators waveguide 16, solar cells 17,18 and batteries 19. Such applications of nanomaterials have been found to depend strongly on the crystalline structure, morphology, and grain size 20 to 25. Although TiO2 and ZnO possess roughly similar value of energy band gap, the two semiconductors found their own application due to differences in their physical and chemical properties. The TiO2 is better known for its chemical stability, high quantum yield and non-toxicity, whereas ZnO is better preferred in optoelectronic devices as light emitter/detector owing to semiconductor large exciton binding energy, high transparency in the visible range and low electrical resistivity. Researchers have paid more attention to the coupling of semiconductors, especially a heterojunction based on two kinds of semiconductors with different energy band structures to improve the sensitivity of photodetectors. ZnO and TiO2 are superior candidates to form a heterostructure junction with better properties than individual ones resulting from the coupling of different energy level structures. Therefore, in this study we have synthesized the nanostructured p-ZnO/N TiO2 films using RF sputtering process for UV application. Various properties of thin films were analyzed by using X-ray diffraction, XRD, to obtain their structure and crystal phase, atomic force microscopy, AFM, for thin film surface roughness, field emission scanning electron microscopy, FE-SEM, for surface morphology semiconductor device analyzer, SDAB1500A, for current voltage, IV, characteristics and ultraviolet spectroscopy, UV-Vis, for optical characterization. 2 Materials and methods. By using RF sputtering process, nanostructured p-ZnO/N TiO2 films have been deposited on glass substrates and on the p-type Si wafer. ZnO, a circular 2-inch diameter target, and TiO2, a circular 2-inch diameter target, has been used as sputter targets for the development of ZnO and TiO2 films respectively. Substrate has been cleaned properly prior to deposition of coating. Before deposition of p-ZnO film, we make aluminium metal contact on glass substrate using physical vapor deposition for making ohmic contact. After making ohmic contact, development of nanostructured ZnO films has been carried out using RF/DC sputtering system from Advanced Process Technologies, India. Coated specimens were annealed for 60 minutes at 523 K to improve the crystallinity of as deposited p-ZnO film. After proper annealing of ZnO films, nanostructured TiO2 films has been deposited using RF/DC sputtering system. Technical details of thin film deposition for ZnO and TiO2 have been shown in TABLE1 and TABLE2 respectively. The structural characterization of nanostructured ZnO and TiO2 film was carried out on Panelidicol Powder Expert Pro X-ray diffractometer. Microstructural characterization with EDX, energy dispersive X-ray spectroscope, was carried out on Nova NanoSem 450 FE-SEM form Fe Netherland, AFM, atomic force microscopy, for topographical study were carried out on Bruker multimode 8IN scan assist mode. The compositional analysis of as deposited nanostructured thin films before and after annealing was obtained with the help of EDX. Electrical IV measurements were carried out on SDA-B1500A, semiconductor device analyzer, from Agilent with probe station SPS2200 microzact USA at room temperature. The optical property of the deposited nanostructured p-ZnO and TiO2Thin films on the glass substrate were characterized on the ultraviolet visible spectroscopy, UV-Vis spectroscopy. 3 results and discussion. 3.1XRD analysis. The RF sputtered polycrystalline thin films were subjected to the XRD analyze as shown in Figure 1, which indicates the formation of TiO2 anatase phase. The intensity of thin films shows TiO2 major peaks around 2 equals 25.3, 48.1, and 53.9. XRD analysis also confirms the formation of ZnO with major peaks at 2 equals 31.581 degree, 34.207 degree, 35.9 degree and 56.202 degree as shown in the Figure 1. The XRD spectrums show that the nanostructured ZnO thin films have polycrystalline hexagonal wurtzite structure with highly 002 preferred orientation. The XRD diffraction spectrum shows polycrystalline structure of ZnO and TiO2. The XRD pattern was taken in the presence of thin film geometry in powder XRD setup, where the beta-nickel filter was used to remove the Ka2 emission peak of the X-ray generator. The crystallite size and the FWHM of the observed peak were analyzed by the Debye-Scherrer formulae. The average grain size of as deposited nanostructured ZnO thin film was found to be 29 nm, whereas 20.7 nm for nanostructured TiO2 thin film. 3.2 FE-SEM analysis. The surface morphology of as deposited nanostructured zinc oxide thin film, Figure 2, annealed nanostructured zinc oxide thin film, Figure 3, and nanostructured TiO2 thin film, Figure 4, were analyzed using field emission scanning electron microscope, FE-SEM. The deposited films were almost uniform, homogeneous, intact and crack-free as depicted in the Figure 2 and Figure 4. Surface morphology indicates slightly grain size increment in case of annealed ZnO thin films, Figure 3. Energy dispersive X-ray spectroscopy confirms the presence of required elements in all cases with no impurities. It is clear from the FE-SEM images that the grains are unvaryingly distributed over the substrate with good adhesion. 3.3 Afm Analysis. The Afm analysis were carried out for both RF sputtered nanostructured ZnO, Figure 5, and TiO2, Figure 6, thin film under the skin assist mode in the multi-mode AFM, where nanometer scale tip of SiC was introduced to scan the sample in the window of 5 micron. Surface roughness, as a component of the surface texture, gives an indication about the quality of the surface. Results indicate that the root mean square roughness value is low for TiO2 thin films due. The root mean square roughness for ZnO and TiO2 thin films were found to be 12.2 nm and 2.46 nm respectively. The results were made in the nanoscope software, and 2D and 3D image has been shown in Figure 5 and Figure 6 for better perception of morphological study. It is evident from the images that the surface of the deposited film is approximately smooth, homogeneous and uniform. 3.4 UV-Vis characteristics. The ZnO and TiO2 were characterized on the UV-Vis spectroscopy for the study optical properties of the deposited nanostructured thin films on the glass substrate. The abrupt absorption on 328 nm wavelength was seen for both of the deposited films, Figure 7. Although, showing the full transparency for throughout visible range in the given spectrum, which infers that these films are good prospects for the UV sensing device application. 3.5 Electrical Characterization. The electrical characterization plays a very important role for the heterojunction diode. In this study the current vs voltage characteristics were analyzed to see the behavior of p-ZnO and TiO2Thin films analyzed by the semiconductor device analyzer by two probe measurement. The ohmic contacts were confirmed by IV measurements. The IV plot of a fabricated p-ZnO and TiO2Thin films in forward and reverse bias conditions is shown in Fig 8. The current was analyzed by sweeping the voltage from -5V to +5V and the knee voltage was found to be around 1.58V, which also compliance with the wide band gap semiconductor material as ZnO-based diode. The current transport mechanism of fabricated structure could be defined with the help of various regions as cutoff, linear and exponential. The different region can be explained in the curve, such as the current is almost negligible till the 1.58V around that would be defined as the cutoff region. Further, a slight increment, almost linear, in the current can be seen up to the 4V. Afterwards the current increases exponentially. On further increasing the voltage leads to the exponential growth in the current, probably due to the charge carrier injection on the higher potential. For conclusion. In summary, nanostructured p-ZnO and TiO2-Thin films have been deposited on glass substrate by RF sputtering process. XRD pattern confirmed the formation of ZnO and TiO2. Crystallite size was in the nm range, which is same as observed from the FE-SEM micrograph. Afm result is also in compliance with the FE-SEM result in order to study its root mean square roughness. All the structural studies have found a good prospect to use the nanostructured thin film for UV application. It can be concluded that the nanostructured p-ZnO and TiO2-Thin film showing a quite interesting results, which incite a very prominent application in the field of UV photodetectors and other opto device application as well. Afm, FE-SEM, and Edx results confirm that the deposited films were almost uniform, homogeneous and crack-free. 5. Acknowledgement. The authors are very grateful to Materials Research Center, Malviya National Institute of Technology, Jaipur, India, for extending facilities for various characterizations.